talk. Okay. um, Welcome to another lecture from the GSM. I am Roger Benepe. I am your president for this year. Um, I want to thank Randy Strobel for hosting this meeting and all those people that helped get this going. There's a couple of things, and again, special thanks to Steve Erickson for finding all these wonderful lectures. They've been outstanding the whole year. Uh, as with all our live lectures, these are free and open to the public. If you're not a GSM member, please open the chat box and type non-member and tell us how many people are watching. We can count the number of devices, but we do not know how many people are actually watching on there. If there's one, there's just one. But I mean, if you have a room full of people, that'd be awesome. We'd like to know that. Okay, let's see some other things. Question and answers will be at the end. If you have a burning question, you can put it into the chat and we will decide if it warrants interrupting the lecture. But hopefully let's try to keep it to the end. It works out the best. If you could use this lecture for continuing, what is it? Continuing education credits, please tell us in the chat and we will send you the form that you need. Okay, a couple of announcements before we get going here. The banquet this spring is going to be in person. It's May 9th at the U Gardens, where we've had it for many years. So that'll be great. I can't wait to see all of you actually in person. The field trip that myself and Steve William are doing is on, and that's May 16th. Dress for the conditions. Keep an eye on what the weather is doing. I'm planning on it being a little on the muddy side. They're getting a lot of rain down there, so just so you know that it does get pretty muddy down there. But it no matter what, you're still going to find lots of fossils. Okay, our next board meeting, which is May 19th, will be at the Minnesota Survey. We are doing in person. Harvey has offered it up to us, so we're going to take it. Use your own discretion on whether or not you want to wear a mask or not. I probably will, just because. Do any other people have any announcements?
I'll just add that we will be sending email about the banquet. A lot of the information is on our website already, but we'll be sending emails the week before, just as I normally do. And it may be that we're looking into also broadcasting at the same time, but we haven't proved that'll work yet.
Okay, that's great. Today's speaker is Cheryl Seeger. She's a geologist of 30 years with the Missouri Geological Survey. She works with ore deposits, and that she's going to be talking to us about that, and with the mining that they're wanting to do in northern Minnesota. This is really going to be a timely topic. So welcome, Cheryl.
Okay, thank you. And we'll hope all the technology works fine.
Yep.
Okay, seeing my screen okay?
Yes, we see it.
Okay, and let me go to, there we go. Okay. So first off, I'd really like to thank you for inviting me to give this presentation. I will warn you that I'll be reading my talk because I'm covering a pretty wide range of material in this. And with that, we'll go ahead and get rolling. The postcards are kind of here for humor in a way, but I do want to note that they're not really an exaggeration, as the Tri-State District was the world's leading zinc producer from 1850 to 1950. The district covers a large area within Missouri, Kansas, and Oklahoma, and went through multiple name changes before being called the Tri-State District eventually in the early 1900s. The district is home to a minimum of 4,000 underground and surface mines that have been documented within the district, shown roughly there, with individual mines often having multiple shafts or pits per mine. And I do want to note that this heavy concentration of mines that we see near the town of Joplin is partly due to the age of the mining, as a lot of it was earlier mining when there were lots of small shafts being done, as well as due to the fact that in Missouri, our database includes the multiple shafts from a single mine as individual records, as well as including tailings data. So that's partly why that has such a concentration near it. So Tri-State is a world-class ore district, and as noted, it led the world in zinc production for a century. It produced more than 22 million tons of zinc and nearly 4 million tons of lead over the life of the district, and was a major supplier for the US for 4 major wars. During peak operations, more than 11,000 people were employed by the mining alone within the district, and at least 3 times that many worked in support industries. The peak was in 1924, and after that, a combination of decreasing prices for the metals and increasing mechanization in both mining and processing of the ores led to a drop in the number of workers needed in the district, although support industry numbers continued to remain high. And as in many other mining areas, a number of present-day towns, such as the ones you see here, owe their original existence to mining in the district, with Joplin being the largest of these. The district is also gaining new interest as a potential resource for critical minerals. The U.S. Geological Survey has identified multiple mineral products that are necessary for U.S. technology and defense that we are currently mostly or completely dependent on importation from other countries. Some of these that are known to occur in Tri-State include zinc, gallium, germanium, and indium. The USGS currently has the Earth Mapping Resources Initiative, or Earth MRI project, for which the Tri-State District is an area of interest. The potential exists for study of tailings material in the district as a possible resource for these elements. And as you can see from the numbers on the slide, there are still considerable tonnages of these materials that remain in the area. The ore deposits in the Tri-State District are what are referred to as Mississippi Valley type, or MVT ores. And this deposit type was actually originally named after Upper Mississippi River Valley lead zinc deposits found in Illinois and Wisconsin. I'll talk more in a later slide about the major characters, or in detail more about what defines an MVT deposit. But right now, just several of their major characteristics are that they're hosted by carbonate rocks, like limestone or dolomite. They formed long after the host rocks, and the ore fluids were basinal brines. And Missouri is also home to several other MVT districts besides Tri-State. These include the Southeast Missouri Lead District, shown here in pink, which is another world-class ore district. The Viburnum Trend currently produces lead, zinc, copper, and silver. The Old Lead Belt produced lead, zinc, and copper in the past. And then the Fredericktown Mine Lamont Subdistrict is another area of Earth MRI interest due to its potential for producing cobalt and nickel. The Washington County Barite Lead District actually was also a world-class ore district and led the world in barite production for a number of years in the 1900s. And then there is the Central Missouri Barite Lead District, which covers a much larger area, but never approached the other districts in tonnages. So what I'm going to cover in this talk, I'm going to hit a timeline of major events in the Tri-State District. I'll describe the host rocks for the deposits and the main ore-related minerals and rocks, describe the shapes and occurrences of the deposits, and then wrap up with the leasing, mining, and processing methods used in the district. So looking at the timeline, the earliest period of recorded lead mining was in Linn County, Kansas, which is located north of Bachelor Springs. This was the earliest recorded. There definitely was at least some lead mining that occurred before that within the district. The earliest known date for lead mining and smelting for shot at the site of Oronogo, Missouri, which is, if I can keep my mouse going, just north of Joplin, was in 1836. In 1851, the first major discovery of size was at what was referred to as the Minersville Camp, which led to the founding of the town of Granby, Missouri. During the Civil War, exploration halted, but almost immediately after the end of the Civil War, exploration and development really boomed within the area. In 1869, the first zinc ore was sold, and this is when things really kind of start rolling quickly. In 1870, discovery of ore at Joplin was essentially the starting point of the growth of the district to national prominence. And at the same time, zinc ore was discovered in Galena, Kansas, which is located just right here in the corner of the state. And by 1872, just 3 years later, zinc was the dominant metal product in the district. In 1877, there was the first commercial lead production in Kansas near the town of Galena. And commercial production really began in Ottawa County, Oklahoma in 1891. And there were also the initial discoveries at Pitcher, Oklahoma, which is located right about there. And Pitcher became very important once major bodies started being produced in 1914. And by 1915, the Pitcher field was producing more than 90% of the ores in the district. In 1916, exploration began in Bachelor Springs, Kansas, with significant discoveries occurring. And by 1918, production in Missouri was dropping quite a bit, partly because it had produced so much of the early ores in the district, as Missouri had a lot of the shallower deposits. By 1926, which was the peak year of production, Ottawa County, Oklahoma became the world's largest source of zinc. In the late 1930s, a lot of modern mining practices, including diesel trucks and mechanized equipment, were introduced, which really helped speed up production within the district. After World War II, production gradually declined. The last mine in Missouri closed in 1957. And in 1970, mining ended in the district with the closing of Eagle Pitcher's mine near Bachelor Springs, Kansas, and the closing of their mill at Cardin, Oklahoma, which is essentially at the same location as Pitcher. So the host rocks for the deposits are Mississippian age, Burlington, Keokuk, and Warsaw formations. These are limestone formations. And oops, losing track of where I am. Okay, the lowermost of these are the Burlington Keokuk limestones. These are actually two separate formations, but in many areas of Missouri, including the tri-state area, they're very similar and have a gradational contact, so frequently they're described as one unit. Burlington Keokuk is a light-colored, generally gray limestone, although it often weathers reddish along fracture or dissolution surfaces, and it does contain some dolomite and variable chalk content. These limestones are really noted for the formation of karst and especially of sinkholes and dissolution of the limestone along fractures. Burlington Keokuk is also known for its very high fossil content and is often marked by high concentrations of crinoid fossils. And it contains so many of these fossils in some areas that its original name in early years of Missouri geology was the incrinidal limestone. The Warsaw Formation, which overlies the Keokuk limestone, is also a gray, slightly cherty limestone that often looks very similar to the Keokuk, especially in southwestern Missouri. Formation contains some shales, although these are far more common in the eastern part of the state than in the western part. It's also noted for being fossiliferous, although not to the same degree as the Burlington limestone. Two of the most common fossils that are found in the Warsaw and that are somewhat diagnostic of it are spirifer brachiopods and Archimedes bryozoans. And spirifers are bivalves that were common during the Paleozoic and are marked by this very strong ribbing and distinct dip in the upper shell. Archimedes bryozoans were also limited to the Paleozoic and were filter feeders similar to bryozoans found in the oceans today. They were named for their distinctive fossils that resemble an Archimedes screw. And here, besides seeing the central portion, you can also see some fossilized pieces of the fan material. So Tri-State was a zinc-dominant MVT ore district with zinc minerals 5 to 6 times more abundant than lead, although the earliest mining in the district was primarily lead. The minerals varied from zinc and lead oxides and carbonates that were mined during earlier years to zinc and lead sulfides, which were mined later in the life of the district. Which minerals were mined at which time depended on both the ore processing methods available at that time and on the depths to which the mining was feasible. One of the major technological changes that led to sulfide ores being mined and zinc becoming the dominant product was the ability to smelt the zinc sulfide or sphalerite ores, which was not feasible during the earlier years of mining. The zinc became so dominant that after 1872, Missouri alone had 17 zinc furnaces operating around the clock. So as noted, the earliest mining was of lead and zinc, carbonate and oxide ores. Besides being easier to process, these were also the ores that were nearest the surface and that could be mined above the water table by the simpler earlier mining methods. So the ore minerals mined at this point include cerussite or lead carbonate, which here we can see is the white material in these historic photos coating galena cubes. Smithsonite or zinc carbonate, and hemimorphite and hydrozincite, which are both zinc hydroxides. The historic records will often talk about dry bone as one of the ores, which was a mix of these. And you can see how from this whitish color and kind of earthy texture, they may have picked up that nickname. And calamine is also often referred to, and that's a mix of smithsonite and hemimorphite. Once the mineral processing improved, most production was from the sulfide ores, sphalerite and galena. The ore was found disseminated or scattered through the limestone, dolomite, and jasperoid, which I will talk about in a moment, and as crystals in vugs or other open spaces. These minerals also had nicknames that were commonly used by the miners in the field, as opposed to calling them galena and sphalerite. Galena was frequently known as shines, due to the shiny silvery color of the mineral when it was broken or crushed. And if you've ever seen cleaved up galena, you know exactly what they were talking about, calling it shines. Sphalerite, on the other hand, was generally called jack or blend and was often differentiated based on the color of the sphalerite. Blackjack was dark colored sphalerite, while the clearer reddish sphalerite you see here was called ruby jack. And the difference in color is primarily related to the amount of iron contained in the sphalerite. Also, sphalerite was not processed during the earlier years of mining. Ore that contained sphalerite was piled on dumps around the mines. This actually led to one of the more unique uses I've ever heard of for sphalerite, as these dumps were used to build stockades to protect the mining camps during the Civil War. So besides zinc, potential critical minerals found in tri-state include germanium, gallium, and indium, along with cadmium. All four elements are either contained within the crystal structure of sphalerite or are found as separate minerals associated with the sphalerite. Besides being found in the sphalerite, cadmium is often present as the mineral greenachite and is seen coating other minerals. This particular photograph shows it coating calcite. Cadmium was produced from the district during World War II, with around 14 pounds of cadmium produced per ton of zinc. Germanium was never produced, but was estimated that every 1,500 tons of zinc concentrate contained about 1 pound of germanium. Gallium, while associated with the sphalerite, has no reported production, although we know it was present. And indium was produced in the past, but production figures are not available. Several other minerals and rocks were common, but were not considered to be part of the ores in the district. Chalcopyrite, which we can see here on dolomite, was found throughout the district. While it is recovered as a copper ore in other mining districts, there was not enough of it present in tri-state to be economic to produce. Pyrite was present, sometimes as crystals, but more commonly found as scattered grains. Quartz crystals were also common in the area, or were found in the area, but were not common. However, quartz as chert was a significant rock type in the district and could be found as thin layers or small nodules, but also as massive beds up to 35 feet thick. The most notable in the area is the Grand Falls Formation, an entirely chert formation named for the falls it creates near Joplin. And finally, both the rock and the mineral dolomite are present in the area, with dolomite often forming saddle-shaped crystals in open spaces in the host rocks. So I mentioned the jasperoid. Jasperoid, found in the tri-state district, is made up of very fine-grained silica that probably replaced the carbonate rocks and also likely formed at the same time as the ore minerals. The dark color of it that we see here is due to bitumen, a thick, dense hydrocarbon that's contained scattered throughout the jasperoid. And in this photo, you can also see grains and crystals of sphalerite with this gold color that are contained within the jasperoid. So grades of ore, if you're not familiar with the term ore grade, it simply refers to the concentration of the desired mineral that the rock contains, with lower ore grades containing less of the mineral and higher grades containing more. Because the potential economics of the ore varied through time depending on the mineral's mined, processing methods used, and the value of the ore, the grade of the ore that could be mined economically varied throughout the life of the district. And one example of this is during the Great Depression, when the dollar value of zinc and lead metal dropped drastically. As you can see from these numbers, the quality of ore needed to make the mining economic almost doubled. Once the US became involved in World War II, the mines could produce much lower quality ore and remain economic. Also, the continuing increase in mining mechanization helped the lower ore lower grade ores remain economic. So I mentioned earlier that I would discuss more about MVT deposits and how they form. They all form from hydrothermal fluids, which is just essentially a hot to warm water that carries metal ions. So at any point during this talk, when I mention ore fluid, that's all I'm talking about is hot water with metal ions in it. The MVT fluids generally ran about 100 to 150 degrees Celsius, which is around 210 to 300 degrees Fahrenheit. They are by definition hosted by carbonate rocks and formed long after the host rocks. For example, the Southeast Missouri lead and zinc deposits are in Cambrian age host rocks, but the ore fluids appear to be Pennsylvanian in age. And if someone wants to ask at the end of the talk, I'll explain why I didn't use tri-state ages as an example, because they're kind of a special case. In addition, alteration of the host rocks is relatively rare. They're generally not affected much by the ore fluid passing through. If you think of, for example, an igneous intrusion coming in and how much heat and fluid would be coming off that, they tend to really cook the surrounding rocks, whereas these fluids are hot but cool enough they don't really affect host rocks very much. And for the fluids to form ores that are economic to mine, there has to be something that causes the ore minerals to be localized. This can be a change in the rock type, a change in the formation, such as an overlying shale that traps the fluids, or it can be open space created by faulting or by karst. Most MVT fluids are assumed to, or most MVT deposits are assumed to have had two or more fluids that mixed, which led to changes in the water chemistry causing the minerals to precipitate. These fluids are generally assumed to have come from nearby geologic basins. So typically for MVT deposits, the ores in tri-state are found replacing the host rocks scattered through the limestones, as well as filling open spaces such as fractures and karst. In many cases, the ore was localized in and near fractures related to gentle northwest trending folds, with the majority of the mineralization occurring in the synclinal portions of the folds as opposed to the anticlinal. In areas outside of the folding, the ore is almost always located in nearly vertical shear zones. Other open space for ore mineralization and ore fluid movement was created by karst, dissolution of the rock, and other dissolution along fractures. Generally, the only alteration seen is replacement of the limestone by jasperoid, which in itself is brittle and fractures more easily than the limestone, and also created more open space for the ore minerals to precipitate. The ores are also stratabound, which simply means they tend to be contained within the same formations or beds in the same general area. And there are three main morphologies or shapes of ore deposits in the tri-state district. And these during mining were called circles, runs, and sheet grounds. So circles obviously are circular bodies. They're generally a downward pointing truncated cone shape that often have strong vertical to near vertical fractures and appear to have originally been sinkholes. They also often had Pennsylvanian shales filling in the top of the sinkhole. Small ones were often mined using underground methods, but because of that overlying shale, they tended to have considerable slumping problems within the mines. The larger ones, such as Orinoco Circle, shown here, and Sucker Flats, both of which were located just north of Joplin, experienced initial underground mining. And here from a historic map, we can see the thick clustering of small shafts that were dug around the Orinoco Circle, with later mining going to open pit, with this being a cross section of the open pit. And you can see the mine reflected on the topo map. It was a pretty significant hole in the ground for mining at that time. Runs, on the other hand, are long, narrow, irregular bodies with a linear trend, as you can see on this map. And in geology, anytime you see a linear trend, the first assumption is that some type of structure, such as fractures or faults, are controlling the ore deposition. And additional support for that here is that the host rocks have had considerable quartz or jasperoid added, and that they are also very strongly broken or brecciated. The runs were important ore producers as they ran up to several thousand feet in length, with widths up to 500 feet and heights as much as 100 feet. And then sheet grounds are tabular shaped bodies that had considerable aerial extent, ranging anywhere from 40 to 200 acres aerially. The thickness of the deposits was relatively constant, which made mining easier and meant they could often be done in what is considered a conventional room and pillar method, where the ore is just followed and mined out and pillars left to help hold up the roof of the mine. Within those thicker layers, the ore was generally in individual layers up to 4 inches in thickness and interbedded with chert, such as we can see in these historic sketches. And at least some of the ore controls for concentrating the fluids for sheet ground deposits included the fractures related to folding of the chert. So moving on to ore production, Tri-State is actually a pretty interesting district in that respect, as it crosses the boundary from very simple individual miners developing mines up to methods similar to those that are used today. So the early mining was primarily in shallow deposits, with the ore found in crevices and openings in the bedrock. Mining was operated on a lease and royalty system that led to numerous small independent operators. Claims were generally only 100 to 200 square feet and were leased from landowners, who were then paid a royalty of around 10% of the return from the smelted ore. This remained the dominant system through the 1890s and continued at a smaller scale into the 1930s. And during this time, many small mines were created that would not have been economic later and definitely would not be under current economic standards. And you can see here just the number of scattered individual piles of waste rock where small individual mines were done. So during early mining in the area, the only real difference between prospecting and mining was whether or not ore was actually pulled out and processed once a shaft was dug. Because most mining was done by several individuals or small companies, numerous small shafts were dug. The individual shafts were often as small as 3 feet by 4 feet. And as the ability to pump water was generally unavailable or uneconomic during early mining, the miners only extracted ore that was located above the water table. Once the shaft was sunk, small drifts or tunnels would be run from the shaft to reach as much ore as possible. Once that shaft was exhausted, miners would dig another shaft nearby and continue the process. And again, you can see, small shaft, 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 scattered small operations. So an ore strike by one miner in an area would often lead to intense development by a large number of small miners, rather than a few large developments by companies, as happened later. And one example of this is the large number of shafts concentrated near the town of Granby. You can just see all those are individual small shafts that occurred. And this map covers one section, or about 1 square mile. As an example, this is mining from the early 1900s. Miners were starting to consolidate more, do fewer shafts. comparing size, that's a section. And bringing up Granby at the same scale, you can see the difference in density of individual shafts that from early to later mining. So once the sphalerite became easier to process and pumping of groundwater from the mine became more readily feasible, mining of deeper, larger deposits became economic. Ore found at depths that required pumping tended to limit the ability of individual or small company miners to operate. And because of the additional expense in the mining, the companies needed to do more exploration by drilling to determine if the investment would be worth it. Also at this time, most mining moved to the room and pillar method. The walls of the mine, or the ribs, were anything from 7 to 100 feet high, depending on the thickness of the ore and the stability of the rock. This also helped determine the spacing of the pillars which were needed to hold the mine roof. And at this time, processing moved to more mechanized methods, which I'll talk about below. And remember kind of the size of the mine on this map when we go to the next slide. So by 1915, larger leasing companies began to buy rather than lease the land from the landowners. And this led to the mining being consolidated into a few dozen larger companies, although small individual mining continued into the 1930s. A decline in prices, as well as the Great Depression, helped solidify this trend into consolidation, as larger companies were the only ones with the available capital to open and develop a mine. And again, think of that small area shown on that previous mine and compare that to one of these much larger later mines. Another factor that helped lead to development of larger and deeper deposits was advances in drilling technology in the mid to late 1800s. As drill rigs could go continually deeper, potential ore deposits at greater depths could be found and evaluated for their economics. Again, however, the expensive drilling helped push the consolidation of mining by the larger companies. Also, the ability to drill horizontally greatly increased the ability of companies to follow the ore trends underground and do better mine planning. So in the earliest mining, ore was crushed before milling by the use of what was referred to as a bucking hammer. And a bucking hammer was essentially a large flat-faced hammer. You can picture a sledgehammer that had a large flat face, usually about 5 to 6 inches square. They would take the ore, put it on a large metal plate, and then crush it to around sand size with the bucking hammer. And if you think back on the pictures we saw of the ore in Jasperoid and ore in chert breccias, you can imagine this was not a very simple process. So needless to say, once automated crushing came along, it looked pretty good to the miners. The first major mechanized crushing method were roller crushers, which are also called log rollers. And these are very simple. Ores fed between two long rollers that roll inward towards one another, crushing the ore down to finer particles. The method still generally worked best on ores from fractures or other open spaces and was not as useful separating the disseminated ores from the host rock. So jaw crushers were the next major method used, and these were a lot more efficient at crushing both the disseminated ore and other ores down to the size needed to have better recovery. This sketch is a cutaway view, but essentially a jaw crusher is a box where the ore is fed in. One side of the box, whoops, apologize, I bumped my mouse. One side of the box is hinged at the bottom and then pivots at the top, continually pounding in and crushing the ore to a smaller size until it's able to feed through the bottom. So moving on to milling of the ores, the original mills, so to speak, on site were hand jigs. And this is a sketch of a hand jig from one of our historic field notebooks. A hand jig was essentially a box with a screen in the bottom. You would put the ore in, you would wash it over a coarse screen to separate out the larger material, then take the finer material that washed through and wash it in a sluice box. So you think of something similar to gold panning, and use that to use the water there to separate the heavier ore grains from the waste rock grains. Obviously, these were simple, easy to construct, and easy to move to a new location. However, they lost considerable ore, either by it being contained in pieces of rock that could not be easily broken further, or by being washed out with the waste rock. So the next innovation was an improved hand jig that you still had to operate by hand. The advantage here was the jigs were suspended in a large tank of water. So you didn't have to worry as much about your water source. Again, you shook it by hand to separate out the heavier ore minerals. And again, it tended to lose considerable ore. The next innovation was a steam jig with mechanization replacing the manual labor, but pretty much retaining all of the same inefficiencies. Its major improvement was the ability to process much greater quantities of ore with less manpower. And also at these stages, mills were often packed up and moved from one mine to the next as the ore was mined out, leaving the piles of waste material behind. So along with the consolidation of mining by larger companies, milling was also consolidated into larger, more mechanized mills. And the district was well enough known at the time that the mills actually became known as Joplin type. Ore was carried by conveyor from a production shaft, a central shaft that all the ore underground was moved to, into the mill where it was crushed and separated. At this point, the processing methods used were recovering about 90% of the lead ore, but still had poor recovery on zinc ores as their density difference with the waste rock was not as great as that for the lead ores. So when recovery really improved was with flotation methods. And these were introduced in the mid-1920s. And these are actually still the primary ore separation method that's used today for MVT deposits. With flotation, the ore is crushed to sand size or almost even down to silt-sized material in some cases and mixed with water. And this fluidized material is then mixed with a reagent and pumped into what is called a flotation cell. And this is a photograph of modern flotation cells. The reagent itself is a chemical that has an affinity for both the mineral to be recovered and to air bubbles. So the ore, water, and reagent mixture is pumped in the cell. It's stirred around and agitated to keep the ore from settling, and air is then pumped in to the system. The reagent then attaches to the grains of the ore as well as to the air bubbles, floats to the top, and the air bubbles coated with the ore grains slip over the edge and concentrate. And that's exactly what you see going on here. And I will guarantee you anytime, if you ever get the opportunity to go on a mill tour, and I am as guilty of this as anyone myself, nobody can resist sticking their fingers in this stuff. You can't help it. It's too tempting. So the flotation cell that we're seeing here is actually in the viburnum trend in southeast Missouri, and it's floating chalcopyrite. In areas where more than one mineral needs to be recovered, the crushed ore and water are cycled through a series of cells. So in this case, if we were recovering the zinc, and that's what was coming out here, this would be waste rock, lead ore, and reagent coming out. It would be mixed with a different reagent, go through a whole cell process, and recover the galena. So in tri-state, they would have had two sets of cells to recover the galena and the sphalerite separately. Most viburnum trend mines use three sets of cells as they collect galena, sphalerite, and chalcopyrite. And then the final stage of ore processing obviously was smelting. Early smelting was small scale. This is a sketch of a smaller smelter, again, from one of our field notebooks. One small smelter may have smelted ore for multiple individuals or small groups of miners. These small smelters, similar to the original small jig mills, were often dismantled and moved as mining shifted from one location to another, and again, leaving the remaining waste material behind. Eventually, similar to the mines and mills, consolidation occurred and companies constructed large permanent smelters to smelt ore for multiple large mines. And these are the majority of the smelters whose locations are known today. So in summary, Tri-State was both a world-class and world-leading producer of metals. Sphalerite and galena were the main ore minerals, although early production focused on carbonate and oxide minerals as they were easier to process. The morphology or shape of the deposit affected the type of mining that was done. The early methods of leasing used in the district led to the development of numerous small shafts in many areas, with the milling and smelting done on site in smaller, often movable operations. Changes in leasing, greater mechanization, and development of deeper, larger deposits, along with other economic factors such as lowered prices in the Great Depression, led to consolidation of companies who also developed centralized mills and smelters. Most mines were underground, even if relatively shallow during the early years, and eventually most were room and pillar mines. And the last mine closed in 1970 after more than 140 years of continuous mining within this district. And with that, I will say thank you and be happy to take any questions you may have.
Thank you, Cheryl. Right now, there's one question in the Q&A, and this would be a great time for people to add more. I have two somewhat related questions I'll start with. We saw pictures of this landscape as it was back in the day. What does the landscape look like nowadays?
A lot greener. But there are still areas that have a lot of waste rock, a lot of old shaft openings around. Especially if you look at a topographic map of Joplin, you'll see areas that are all built up nicely with subdivisions and other areas that are just kind of open. And those are areas that, you don't want to build. There's too many little shafts. I know after the Joplin tornado, they had a heck of a time finding a place to build a new hospital that they wouldn't be over old mining. So yeah, like I said, it looks a lot greener, but there's still areas that have a lot of problems.
So you wouldn't call it a very scenic landscape, it sounds like.
Not in specific spots, no. On the other hand, if you like poking around old mine shafts, it's great.
Sure. And then a more general question. It looks like there's potential for a lot of pollution from all these old mines. What's the situation there?
The situation is there's a number of super fun sites there.
I can't say I'm surprised to hear that.
Yeah. Part of that is due to, I didn't say it outright during the talk, but remember when I mentioned all those movable mills and smelters that left their waste material behind that you don't really know exactly what was there? So there's contamination from those, from the processing. There's contamination from smelters, just what comes out of the smelter. And then there is also contamination because of a lot of use of the tailings. There was a tendency for a long time when here is all this nice crushed limestone and dolomite, let's spread it for ag lime, which also kind of spread around a certain amount of contamination. And some of the chat waste material made really great driveways. So it kind of wandered all over the place. I will say, though, that with the age of the district, one of the problems EPA has always dealt with on it being a Superfund site is in yards determining if the lead contamination is from mining or from old lead paint on the house. And that's a real differentiation problem for them.
Okay, thank you. And then I'll go to questions that people have typed in now.
Okay.
But from Nancy, are there any records of early miners developing lead poisoning?
I do not know of any records of that. They must have. I don't see how they could have not, but I don't know that anybody really looked for that in the early years of mining.
Okay. From Diane, I know I can look it up, but what are the new minerals gallium, germanium, and indium used for?
Oh boy. To be honest, I would have to look that up as well. But there are definitely things, a lot of the things that the USGS is referring to as critical minerals, and you can go Google critical minerals and see the whole list. But most of them fall into either defense technology or, interestingly, green technology. It's kind of like if you've heard people talk about the rare earth elements, which we pretty much entirely import from China. You can't build a wind turbine without rare earth elements. It's kind of a little catch-22 that you can't do your green technology unless you go mine this material.
Okay. And also from Diane, you mentioned calamine. Is that actually where calamine lotion comes from?
I believe it is, because a lot of what's in calamine lotion is a zinc oxide compound that helps dry up poison ivy and such like. So yeah, those two are tied together.
Okay, and then another one from Diane. You asked us to ask about the ages of the tri-state deposits. Please do tell.
Okay, the tri-state deposits are really fun. One of the things they can do to help date when ores form is look at the isotopes that you find in lead. And you can look at different ratios of the different isotopes and get ages. And that's how we know, for example, in Southeast Missouri in the viburnum trend that, the host rocks are Cambrian, but our galena is all Pennsylvanian in age. Tri-state has these quirky things called J-leads for Joplin that nobody entirely understands yet, but they give dates that are older than the host rocks, which means if you go by that, you had the ores forming before the host rocks formed, which is kind of impossible. So the ages of those ores is still kind of a mystery to everybody.
Okay, thank you. Question from Mike. At what point in geologic time were there hydrothermal fluids circulating? Thank you, great talk.
Well, thank you. The answer to that is geologic time. I mean, hydrothermal fluids are still floating around today. But think of a hot spring. All a hot spring is a hydrothermal fluid. And all hydrothermal fluid means is hot water. So they've, as long as we've had water, we've had hydrothermal fluids. Good question, though.
Okay. I don't know if Mike was referring specifically to the ones that in the tri-state area or not.
Yeah, and again, we can't really date
Sure.
the fluids because we can't date the leads.
Okay, here's a question from Mary Helen. Given that these were frequently small-scale operations, probably without health protection, what kinds of health problems were prevalent among the miners historically? And are those health problems continuing locally?
Again, you know, in the 1800s, nobody worried about health problems. I hate to say it. So there, you probably would have to talk to somebody on the history side who would deal with health to be able to answer that. So far as, I mean, mining in tri-state is not going on anymore. I do know that in the viburnum trend, they do periodic blood level lead tests to make sure miners are not getting exposed to too much lead.
Okay, and a question from Harry. Are the tailings from the earlier processing such that new methods can extract more of what is wanted?
Possibly. That's one of the things that needs to be studied. But recovery methods are always improving. So that's one thing the USGS is going to be looking at is first off, identifying how much may be in the tailings and then working with various groups to see if it can be recovered. So that is still totally in its infancy at this point.
So basically, it's all research now and no active work in that area.
Right. Yeah.
Right.
Mm-hmm.
Okay. A comment from Alan. I think he's referring to those metals that we talked about earlier: gallium, germanium, and indium. And he says, "I think they are rare earth elements used for high-powered magnetics."
They could be. Yeah.
Now a question from Matthew. Is the town of Pitcher still closed off? My mentor was a miner in the district back in the mid to late 60s and worked in the Canoyer mine, and I've always wanted to see the town personally.
Oh boy. That's a different state. I don't know if it's still closed off or not. I know something I was looking at kind of while putting together this talk, it sort of referred to it as a ghost town. So I don't think there's many people living there. Same thing with Baxter Springs, Kansas. But if it's closed off, I have no idea. I'm sorry.
And would it be closed off because it's just dangerous because of all the open pits, or because of the all the material that's around, or both?
Probably both. You know, if there's considerable lead contamination around, and then also if there are collapse issues from the mines.
Okay, I'm going back to the top now because for some reason there's a bunch of questions from Ronald that get stuck at the top of the Q&A, but I will get to them. How important were mining engineering graduates from MSM to the development of these mines after 1876?
Hugely. I think that's probably where most of the mining engineers were coming from in the district at that point, because we'd have been the main mining school around. When I say we, that's because MSM was Missouri School of Mines, which became University of Missouri Rolla, which is my alma mater, which is now the Missouri University of Science and Technology. So we were this was the main mining school at the time.
Okay, and then Ron also has a comment about earlier, gallium, indium, and the other elements you mentioned are used in fabricating computer chips using a molecular beam epitaxy process. So, so used for computer chips too.
Okay.
So let's see, have we gotten all the questions? I don't see any more questions. This is about your last chance to ask a question as we're coming. Oh, I see a 12 there. Okay. One just came in from Mary Helen. Are you having sinkhole problems in the area now?
Yes. I'm not sure they happen as often as they used to, but periodically, you know, part of a parking lot or something disappears. And I know our land reclamation program here in Missouri does a fair bit of work done in the Joplin area. You know, looking at you know, somebody seeing their foundation cracking, is there potentially an old mine underneath, things like that. So yeah, it was shallow underground mining, so that certainly is a problem.
So are most of the sinkholes because people are building on top of old mines, or because it's a karst area which tends to have sinkholes anyway?
It's a combination. Because yeah, that's one of the things they try and look at is you know, is it a naturally occurring sinkhole or is it a mine? Because if it's a mine, you can sometimes get federal funding to help fill it. If it's a sinkhole, you're kind of on your own.
Okay.
Cheryl, Steve Erickson, how you doing? They did a very nice job. Very good summary here.
Well, thank
we're
you.
looking at mining here in Minnesota potentially. What sorts of lessons can we pick up from that area? What can we be aware of? What sorts of things, leftover tailings, and how much water pollution, and is there a lot of water processing they have to do for the towns in the area? What's the status there?
Yeah, I mean, obviously they have lead issues in the groundwater there. On the other hand, probably if nobody had ever mined there, you would have lead issues in the groundwater because you have a world-class, you know, ore deposit area. It's kind of hard to compare tri-state to modern mining because so much of tri-state occurred before we had any regulations. You know, state regulations for so long primarily just dealt with trying to make the mine safe, as opposed to looking at environmental issues. In that respect, the environmental issues compared to tri-state were relative newcomers. So I'd say the main thing is just kind of the scale of mining and what regulations are in place. And, you know, just making sure regulations are followed, environmental impact statements are done properly, things like that. Again, those were things that just did not exist for most of tri-state.
Sure, that sounds, yeah. It sounds kind of obvious, but no, I think that's a very good summary right there. And it's going to be a hot topic here in Minnesota for a long time. So, anybody want to follow up on that one?
There is another question here from an anonymous attendee. Does he or she asked, do you recommend traveling to the area? GSM field trip.
I mean, it's an interesting area to go see, you know. It's kind of the part of the Midwest that would have resembled, you know, your vision of an old Western mining camp. you can read some of the old records and they talk about, the lawlessness and women being unable to safely, sorry, I got to turn my light back on. It turns off on me. It being unsafe for women to walk unescorted. I mean, it was kind of the Wild West back when. So
And so, I mean, if there's no, I assume there's nothing like a state park that kind of highlights the history of the area or anything like that. Do you agree or not?
there's not a state park, but Joplin has a park. I believe it's called Schifferdecker Park, that has a lot of mining history information and has really, really gorgeous mineral samples from Tri-State in it. It's worth a stop if you're ever going that way.
Okay. And there's a comment here from Diane, which echoes my feeling too. Thank you. Enjoyed your talk about an area I don't know much about. And I'll add, I grew up in Illinois across the river from St. Louis. And the first time I heard about Tri-State was when Steve brought this up as a topic.
Yeah. Well, thank you. And thank you for inviting me.
One more question from Diane here. And what is your state fossil?
Our state fossil is a crinoid. It's a Pennsylvanian one, unlike the ones you see in the Burlington, but it is a crinoid. And oddly enough, our state mineral is galena.
Yeah, we're in the process of trying to get a state fossil named here. We'll see if it happens.
Yeah.
And from Nancy, thank you. I learned a lot.
Well, thank you.
Steve, you want to finish it off?
Well, I want to thank everyone for coming tonight. This is just an idea. I know I lived in Tulsa and I went through Joplin a couple of times and we stopped at some of the mineral museums down there. Fascinating places to stop into. And it's a interesting situation because, like I said, it parallels what we're looking at now. So if we can pay attention to what was done there, maybe it's something we can prevent, or maybe we can't do it. I don't know. I'm not enough of an expert at mining to give the full story, but yeah, just an interesting area. And thank you very much, Cheryl, and thank you all for coming out tonight.
Hey, Steve, you want to mention what we're doing in 2 weeks?
In 2 weeks, Julia Steinberg from the Minnesota State Survey is going to be talking about a asteroid strike in Dakota County. So check it out. Have a good night then.
Okay, goodbye, everybody.